Welcome to this measurement study of a process, Lesson 1. The hypothetical problem. Let's say we have encountered a problem on an assembly line. Let's look at this hypothetical problem. The assembly line operator has found that some tubes from a box of 50 don't fit correctly over a spigot in the vehicle. They are rattling when they should be a snug fit. We know that the spigot is dimensionally correct. The tube is dimensioned in millimeters as shown. We can see from the dimensions that the tube has tolerances on the length, the outside diameter and the inside diameter. The length and outside diameter of the tube have much larger tolerances than the inside diameter. We know that the problem is due to the tube rattling on the spigot. We can therefore suspect that the inside diameter on some tubes may be larger than the tolerance allows. We need to prove this. As the bore has a very small tolerance, the tube has to be bored out on a boring machine to make parts within the tolerance. We need to investigate the problem. Let's start by measuring the bore sizes in the batch of 50 tubes. Now we have 50 bore measurements and they are in the table below. Here we can see the bore diameter, which was dimensioned at 36.32 plus or minus 0.05 millimeters. The table shows 50 results of the measurements that we've taken. As a set of numbers, it is difficult to see any pattern. Within the table, numbers 30 and 37 were outside the tolerance, but were they easy to spot? A way of obtaining a pattern is to group the measurements according to size. So let's draw a tally chart. The tally chart groups the measurements together by size as shown. The two parts that were outside the tolerance are now easier to detect. We can see two results at 36.38 millimeters. At this point, we can see easily that there is a problem with the bores. So let's take our tally chart. We can total up the number of bore sizes found at each size. And the tally chart shows patterns. And we can obtain the range, 36.32 millimeters to 36.38 millimeters. We've now turned the tally chart into a frequency chart. If we turn the frequency chart on its side, we can represent the tally chart as a histogram. If we now draw a smooth curve through the top of each column, we get a bell-shaped pattern. The bell-shaped pattern is fairly typical of most industrial processes. There is a central value at the highest point of the curve, and the pattern of results spread out equally on both sides of the central value. The further we move from the central value, the fewer values we should find. This bell-shaped pattern is known as the normal distribution. Let's go back to this data for a moment. We plotted the data and made a bell curve, but was all data within tolerance? The data that we saw for the bore showed that 2 parts were out of tolerance. We know that the boring machine produced 2 parts out of 50 that were incorrect. So there is a problem with the boring process. No industrial process or machine is able to produce consecutive items which are identical in appearance, length, weight, thickness, etc. The differences may be large or very small, but they are always there. The differences are known as variation. This is one reason why tolerances are used. Let's look at process capability. Here we can see a capable process. This is where the process spread of results is inside the specified tolerances. By comparison, here we can see an incapable process. This is where the process spread of results is outside that of the specified tolerances. The bell-shaped pattern, known as normal distribution, is one that we would expect to see where the machining process is under control. We call this a capable process. We have confirmed that 2 bore sizes were out of tolerance, so we confirmed that the boring process is not a capable process. Now, how do we solve the problem and ensure that all parts are bored out within tolerance? Discuss in your class how we could ensure that all parts would be in tolerance. In our next lesson, we will look at what a process is, process variation and the common causes of variation, and statistics. All of this will lead us to understand how to control a process and not make parts out of tolerance.